Sounds good. Let me just introduce you guys. So our next tutorial is understanding how microarchitecture impacts microservices. This is with Ashraf, Mahgoub, Harshad, Sane, and Kshitij, Doshi. So let me just take a moment to introduce these speakers a bit more thoroughly. So Ashraf is a cloud software engineer in the Cloud Engineering and Solutions Group at Intel. His technical expertise is in designing and implementing automated systems for resource management and performance optimization for cloud-native applications. He has a BS and MS in computer engineering from Cairo University, obtained his PhD in computer science from Purdue University, and his interests span cloud-native systems, automated performance optimization, and self-aware and adaptive computing. Harshad is a performance engineer in the data center and AI group with a deep technical expertise in system software, memory, and CPU architectures at Intel. He specializes in performance monitoring, software optimization, tool development with focus in the cloud domain. Harshad joined Intel as a college graduate in 2008 after receiving his MS in electrical and computer engineering from UC Boulder. And I apologize for butchering your name, Doshi. We lovingly refer to Doshi because his first name is infamously difficult to pronounce. He also works at Intel in the data center and AI group, where he focuses on performance optimization of workloads and cloud instances. He obtained his undergraduate degree in electrical engineering from IIT Mumbai and his MS and PhD degrees in electrical and computer engineering from Rice University. His research interests span distributed systems, memory and storage architectures, and resource management. So a powerful trio in the world of cloud microservices. We're excited to hear all about it. With that, please take it away, guys.
Well, thank you, David, for that for those introductions. I am Doshi, and delighted to be here with my colleagues Ashraf and Harshad. So what we are going to do today is share with you our experiences and thoughts about performances of microservices based solutions. And so these are solutions in which you have multiple components of a larger application talk to each other explicitly instead of behaving like modules in an application that invoke each other's functions. And this kind of loose coupling leads to much better solution velocity because it reduces the explicit software dependencies and simply moves it to the dynamic integration of those services in operation. Now, while it simplifies a programmer's life, it does make let's just stay on the first slide for a second. It does create some performance challenges with regarding to inquiring into what is causing a performance issue or what kinds of things are available as performance improvement opportunities. And in particular, this becomes a challenge with microarchitecture because a lot of hardware level capacities do factor into performance, but they are very hard to track with typical software tools or operating system metrics. So we're hoping that that our tutorial today sketches out some helpful directions in this regard. So with that, let's go to the next slide. So the motivations for this tutorial are three. The first is to figure out when is it better to consolidate microservices because each microservice by itself doesn't consume the whole platform because it's a small application typically. And we want to be able to achieve better multiplexing of hardware for such efficiencies. Now that is balanced by the fact that these are complete containerized services by themselves with a significant amount of their own resource management. So figuring out how exactly to allocate resources amidst competing demands particularly when these microservices depend on each other for their continued progress. That becomes a challenge and impedes performance and predictability. And the third and major issue is that very often at low levels of resource utilization, typically don't have significant evidence of these microservices if they are co-located on the same host, interfering with one another with regard to resources. But as the system load spikes, that can become a problem because there can be resource related performance interference between them. So those are the three motivations that we'll double click into in this tutorial. Let's go to the next slide. So the organization of the tutorial is it's in 4 parts. In the first part, we will talk about what is it that makes the performance of these microservices challenging. We will highlight the importance of figuring out what are some of the similarities and differences among these characteristics among these microservices characteristics at a hardware level, so that we can use that information in order to make some intelligent decisions about co-locating or migrating when contention arises. We will then recap a presentation or a tutorial that we had given last year, which was on the same topic of microservices, but at that time we were coming in more from a top-down methodology, and we had sketched out that as a map and zoom methodology. So we'll recap that briefly, and then in the last but most significant part of the tutorial, we will talk about open source tools that Intel is delivering in order to help developers at large and people who are trying to optimize cloud performance of microservices. So let's go to the next slide. So what are microservices in a nutshell? For a long time, right, when you have an application containing many different components, the emphasis is to try and achieve modularity by various kinds of techniques like information hiding, separating concerns, and so on. But that's not always easy to do. Here we are showing a kind of an example of an application that might have multiple different components with some components forming the core of the application. Let's click once. And Harshad, if you can click once. Yeah, so that's the application core. And then that also has, the other components might be mostly loosely coupled with the application core, but they are all part of the same monolithic application. What that does is that any software API, library version types of dependencies amongst applications, as well as the need to scale certain components independently from one another, becomes a challenge with respect to fielding this monolithic application in the field, and also in evolving it speedily. So let's click once or twice, and so the transformation that microservices achieve is that that all of these components are pushed into their own separable containers, with the interactions between them and the core business logic of the application being streamlined and made explicit, so that each one of those independent pieces can evolve independently and scale independently. So that's the general very high level introduction to microservice architecture, and what it brings with it are as I indicated at the start, various performance issues and landmines. So we are going to really focus on just 3 here, but there are others. The 3 major ones are that there are time varying dependencies and demands on resources. There are trade-offs between co-locating and scaling, and there are observability challenges. Let's click through each one of them in turn. The time varying demands refers to the fact that very often coordinating allocation of resources is kind of a distributed scheduling problem, right? Because you're allocating these resources, and these resources are typically taken back or recycled at fairly coarse-grained time boundaries. And so, in other words, this resource allocation is loosely coupled amongst all of these microservices. And so, if there are changing patterns of resource demand, or as time varying loads cause allocation strains, and we have that problem with regard to honoring the dependencies between these microservices, where one microservice depends upon the other in order to make its forward progress. The second set of issues have to do with co-locating and scaling. Generally speaking, there will be different peers different sets of peers that interact with each other in a very high bandwidth, low latency fashion, or that would be the ideal condition for them. And then there are others that are generally speaking less chatty with each other. So it's very attractive to co-locate these peer microservices that exchange data frequently on the same host. However, what that does is that when you need to scale, you cannot scale them together on the same host, because ultimately there's a finite amount of host resource budget, right, that needs to go into satisfying all of them. And then the third set of challenges is observability challenges. Trying to observe what goes on at a hardware level on a monolithic application is itself a challenging task with a lot of time varying situations. But when we have many different microservices, right, this problem compounds. And in addition, the performance of a microservice chain typically is dominated by concerns about tail latencies, where an entire chain is able to collaborate efficiently in order to perform a request on time. And this becomes a problem with monitoring and drill down, because yes, you could in theory observe everything, but doing so at low overheads is a big challenge. In the next 3 slides, we'll inquire into each of these three in a little bit more detail. So let's go to the next slide. So the one pain point of managing the performance of microservices is the communication scheduling effects. As I just said, co-locating communication intensive peers on the same host may improve message speeds, may help us with network efficiencies, but obviously there are resource contention issues when things are co-located. And then, as we said, these are aggravated by sequential dependencies among distributed steps. In other words, what really happens is that while the architecture achieves loose coupling at a software level, performance essentially becomes much more tightly coupled between these things, and especially performance when it comes to resource allocation. That is combined with complicated by the fact that there may be the host operating system and the hypervisor environment, or the environment within the next level of scheduling that is trying to multiplex a set of hardware resources amongst all of these microservices, and therefore there's frequent allocation and reallocation of, for example, CPUs, and that can lead to scheduling and multiplexing delays. And then, of course, the weakest link problem, where the slowest or the most jittery microservice ends up affecting those that are coupled to it by either execution dependencies or resourcing dependencies. So overall, the challenge is determining when and what to migrate, when or what to consolidate, and how to scale. The next set of the next pain point, right, is the noise or interference and its variation with load. Interference here we are talking about is resource interference, where let's say, for example, one microservice incurs a significant amount of cache misses and proceeds to create a significant of pressure both on memory bandwidth as well as on cache capacity, and that affects one of its peer microservices. So these kinds of interference at the hardware level can occur at many different levels in CPUs, in private and shared caches. There can also be capacity and contention related latency, where the latency that one observes for a memory access being completed after it misses the caches can vary according to the amount of demand, right, that is being placed on the total memory bandwidth. You also have some software challenges where page cache becomes a point of contention amongst microservices that may not be using too much CPU, and therefore may be chosen as good candidates for co-locating together. But their collective memory demand exceeds what the platform can provide. Similar thing with memory bandwidth, network and storage bandwidths, and so on. Now, these degrees of interference may change also over time when the request load changes from causing low utilization of various resources to much higher levels of utilization. So that can happen simply because of load shifts. That can also happen because of inherent multiple phases within microservices. How does one keep track of all of this, and how does one do adroit management of resource allocation? That becomes an issue. And what we want is that the monitoring and profiling tools should be load aware. The third pain point that we can click into is the limitation of existing observability tools today. The first is the fact that when you've got a lot more entities to track and monitor, you have high overheads. You also have non-existing or shifting baselines, because unlike a monolithic application, it's very difficult to say that under these under this set of host resources or under this set of operating system tuning, that we were able to achieve a certain baseline performance, and then we can measure where we are with respect to the changes in that baseline performance. You can do this for one microservices at a time, but how do you do that for an entire system or for multiple microservices? And then you have the classic problem that a lot of performance tools today tend to be very throughput related and throughput centric, whereas most of the tail latency excursions arise exactly under some conditions that are anomalous and that are not frequently, that they don't necessarily come up frequently. As a result, current tools that are very throughput centric and therefore average behavior centric have difficulty with exposing causes of tail latency excursions. So now the other complication, of course, is that the number of microservices is potentially infinite, right? I mean, it's a huge combination of different microservices. So how does one make this problem tractable and scalable? Well, we try to reduce the dimension of these differences by grouping these microservices into separate groups according to what their behavior characteristics are. And this is where the notion of workload similarity emerges. They're loosely defined workloads that are performance sensitive to a similar degree to a limited supply of the same types of resources can be considered to be informally quite similar to one another. And so once one can map that out, right, one can use that in order to reduce the size and scale of the problem. So let's click once. So knowing that you have got two microservices that are very similar, it naturally makes sense to either place them on different hosts or monitor what's going on and migrate one of them when that whatever that limited resource is that they are heavy demanders of approaches saturation. And then if you want to really keep them together, then you want to do joint capacity planning. And then when you have dissimilar microservices, they are obviously co-located more easily due to their diverse stresses. And then one more click. And when two microservices are similar, as measured by their performance signatures or resource consumption signatures, then one can apply kind of transfer learning to what has been done for what has been to optimize one, what has been done configuration wise in order to make one and utilize the available resources better, right? And those things can be transferred from a known workload to an unknown workload if the two workloads are similar. So with that, let me invite Harshad to take over and take us to the next set of slides.
Okay, thank you, Doshi. Thanks for setting up the background. To continue from where Doshi left off, we are now going to start delving a little bit into the solution space. And we'll start with the topic of similarity of microservices. Here we are going to talk about microservices or any application as a workload. And we want to be able to firstly identify the similarity characteristics. What are the things to monitor to decide whether an application or a microservice is similar to another microservice? And I'll use the term as a workload, because microservices can be part and parcels of multiple workloads. So the option, although there are many ways of doing it, the option that we have chosen here is to be able to use it from a microarchitecture approach, which means imagine that you would be able to take your eyes and put them into the processor and visualize the world from there. What would the workloads look like? What would the kernel, the application look like? And what are the resources that they'd be using? So imagine something looking at from a processor level as to what are the resource constraints when a workload runs. If we are able to have multiple of these in an n-dimensional space, right, we'd have a lot of workloads, and for each workload, we'll have a lot of metrics. Imagine things like your cache utilization, your memory utilization, your cache-to-cache transfers, your execution units, how your registers are used, all those things, if they can be created into attributes for each of these workloads, such that we create a signature of such workloads. And then later, because there are too many dimensions and too many metrics here, we use dimensionality reduction approach to basically reduce this down to simple things like, hey, is this workload front-end bound? Is it back-end bound? Is it stalling? Is it non-stalling? Is it into lock contention? Very basic tree. And I'll show what that tree looks like. But if they are then mapped onto two dimensions with PCA for visualization, can we do some similarity analysis on them, right? And I'll give you an example of what metrics or what that tree looks like. So these are the criteria used to develop that signature of that workload. Remember, we talked about eyes in the processor. This is what a processor is going to look at when a workload executes. It's going to say, hey, there are only 4 things that can happen if I'm executing. Either I'm executing cycles or I'm not executing cycles. If I'm not executing cycles, those are just not halted cycles. But if I'm executing cycles, I can either be front-end bound, which means I'm trying to execute. I'm trying to get my instructions into the queue to execute, or I am actually back-end bound, which means I have passed my front end. I have done all my instruction fetches, branch predictions, getting those instructions into the execution unit. But I'm waiting on executing them because I'm waiting for data coming from the cache, from memory, waiting on some contention to resolve, and that will all fall under back-end bound, right? And then there will be another couple which one would say, hey, I just made the wrong decision because I speculated something wrong and I have to flush my pipeline and I have to reissue all my instructions. Or you could be retiring, which means that's the best case where everything's done and my instruction has completed. And under each of these, you would have different objects, and basically you form a tree with this and essentially form a signature for a workload. Imagine if we were able to do that and then do dimensionality reduction on that for several of these workloads and plot it on a two-dimensional PCA chart with the two axes X and Y being two principal components, and each dot in here represents a workload with the subset of the characteristics that we talked about in the previous slide as its principal component. So what you want to see, what you're seeing here are blue dots, which is essentially your spec CPU workloads. And you can clearly see that second CPU forms a very distinct cluster towards the right. Now, although this is PCA and this is, dimensionality reduction, I can, we've provided arrows to show, hey, these services are front-end bound or these are back-end bound as you move towards the left side of the x-axis, and as you move towards the right, they're retiring. As you move downwards, you're front-end bound and so forth. So what this cluster is telling us is spec workloads are literally micro benchmarks. They have no dependencies per se. They just maximally try to get the most out of the CPU or the memory subsystem. If you compare these with real workloads, or the ones in green, which are open source workloads but with synthetic data that we have downloaded and run, like Memcached, Aerospike, Death Star Bench, which is an example of a microservice and hotel reservation within it, and so on and so forth, they form a different cluster. And then there's another spec cluster which has vectorization components, and that's why it forms a separate cluster. But you may see that spec components are nowhere closer to what real world workloads are. But the point of this exercise is to be able to establish the similarities and dissimilarities from the processor's signature point of view. Right. Okay. So now let's do a recap from the last time we did this tutorial, but this was from a different point of view. It's called map and zoom, a methodology for microservices. And we described a very specific method of going top to bottom into the microservice and how to analyze the bottlenecks that Doshi was talking about for these microservices. And we'll also talk about the tools that Intel has developed and open sourced in regards to each one of these. So the first one is called health check. We all, irrespective of what the issue is, or there is no issue, or you just want to find out where resources are being spent, the first thing that is done is an health check. And the health check basically is a software and hardware health check. And I'll talk about it in each of these in the next slides. The second one is called as a component breakdown, where you take the big microservice and you want to break it down into its sub pieces, because as we discussed, observability is another pillar, which is a hard part of microservices. So the component breakdown will allow us to basically characterize each component separately, find out the non-scaling or the non-performant components from the performant components. And then once we have established the non-performant component, we'll deep dive into performance characterization of it with tools that I'll describe, with software profiling and identifying non-scaling components. So the first one is an health inspector. This is a tool that Intel has open sourced. It goes all the way from checking your BIOS, your firmware, your CPU information, OS settings, even what applications been running, sensors, versions of applications. It can find out whether a version of, let's say, a Python application running, is that most compatible with the CPU architecture running, or should you have upgraded it to make sure you make use of the best ISA. It has a recommendation tab that comes up and says, hey, this is what we found on the system, and these are the things you can improve from what has been seen. As a part of it, it will also do micro benchmarking, and it will give you what is the system capable of at its maximum, and also health check on utilities, the kernel versions, and so forth. This is just an example of this is not in the cloud, but an on-prem customer where the DIM population, right, how the DIMs are populated on the platform were done in a haphazard way versus later when it was identified. And this is the picture and one single HTML page that comes in after you run this 2-3 minute of the health checker. And it tells you, hey, you should have, put the DIMs in a certain way, or there is one DIM which is from a different manufacturer, or the speed is not matching. And because of that, it also plots the memory bandwidth versus latency curve, and you can quickly find out, hey, this is my first system one, its latency curve is not looking as great as what it's supposed to be, which is my reference, which is yellow. And then after we made the change, it fell down to the red, right? Lower the better, because the y-axis being latency. So this is just an example of an hardware feature. There's also a lot of software features that we find during the health check. Once the health check is done, we first want to make sure, since the microservices spans a lot of clusters and it has got a lot of moving pieces, we first want to be able to know where to drill down. right? That's the first piece, because when you run a query and instead of the regular X seconds that's it taking, let's say the P99s suddenly increase, where do you start? So the way, instead of using traditional instrumentation, for example, like Jaeger, where you have to go and make changes to your source code and do instrumentation to find where your latency is, because software changes so fast, the mitigation is to use eBPF at runtime and be able to filter out these raw interactions. This is an example of a chart that comes out when we run such a tool. It's based on an Intel concept tool today. It's still in progress, but what you can see is this is the TCP instrumentation to show interaction between various services. This was the Death Star bench workload, and as it was running, you can see OpenResty talking to a unique service, talking to Compose Post service, to the Redis server, and the arrows are basically the time spent between them through the TCP instrumentation that it does, right? So now, based on this, we can actually find out which arrows are the most hot based on the color coding that we do and say, hey, looks like OpenResty and user service seems to be the one spending most of the time. We would like to go in and instrument where they are running, look at the hardware, look at the software, and be able to understand what's happening in those services. This whittles down this, this is a really small chart. If you go into a real Death Star bench, like, services where some customers run, it's very, very important to find out these pieces before moving on. Once we know what we are looking, which service we are looking at, now we want to put that eyes back into the microprocessor and say, and use an excellent feature in the processor called as the PMU, which is known as the Performance Monitoring Unit. And it can monitor hundreds and hundreds of events related to CPUs, caches, memory, UPI, NUMA, and attribute them to the software to say, hey, here's my contention issue. And characterization initially is done at a system level. So at a system level, you want to know, am I under cache pressure? Am I under CPU pressure? Am I under contention issues, synchronization between threads, from the perspective of the CPU? So, I'll show a demo of a tool in the end that does that, but just an example of because a processor is a very, very complex piece of hardware. You can see, you can basically use perf to get all this information but look at the command that you have to go through, right? It's not practical for a person to each time come up with this and figure out, hey, where in this pipeline of this is called front end or my execution engines or my memory subsystem, where am I bottlenecked? We want to make this easy for you to understand where are your stalled cycles and where are they being spent in hardware. And I'll provide a demo of this tool. And once we know where we are stalled, let's say it was some cache pressure, right? And it was LLC misses that were happening in that piece of software. And that's why we were getting that big red dot around one of the services in the component breakdown. Now, we can do software profiling. Usually, developers do tend to jump into software the moment they find an issue, but it's important to go through this process because now we have the information of exactly which service. We have the information that this is LLC misses causing it, and now we want to profile the software stack with LLC misses in mind, not just CPU cycles, but with LLC misses. So if you've seen a very popular article from Brendan Gregg and a GitHub tools called as flame graphs, you can use that visualization approach, which uses CPU cycles to visualize them. But imagine that you could use L3 misses and then profile and generate the flame graphs. You'd exactly know who your issues in source code are, and then go into how to be solving them. Here's just an example of what a flame graph looks like. Many of you may be familiar, some may not, but this is an example of a flame graph taken on Kafka, and it shows a lot of time being spent in SSL. SSL is just the security layer where encryption is being done. And if you're not aware, Ice Lake processors from Intel have got a new ISA, which has got new instructions to do crypto. And we've got software libraries that make use of these, and simply moving this Java version from 8 to 11, where the software libraries are used, provides a huge benefit in the order of 2 and 3x sometimes, based on the algorithms. Those were examples. The other, and one of the last examples of identifying poorly scaling aspects is where am I having the scaling bottlenecks? So we can do frequency and core scaling aspects to figure out, hey, did I have a problem because I went from 4 to 12 cores as my application scaled? Or did I go to an instance in the cloud that was not the most optimal instance for my microservice? So with that, I'll move on. And I think Ashraf, you can take over. Thank you.
Thank you, Harshad, and thank you, Doshi. So the next slide, we will discuss what are the primary objectives for our monitoring tools. The first objective is to be lightweight, and this is beneficial for both the tool itself, achieving high accuracy, and for the tool to not become a noisy neighbor for the running workloads. And as you would imagine, that reduces the noise from the microservices on the tool would provide a higher accuracy for monitoring and detection of performance bottlenecks. The second objective is to have a short response time to be able to respond quickly to performance bottlenecks or interference happening between the workloads. And this, of course, is very critical for latency sensitive applications. The third objective is to have an adaptive depth instrumentation. And as Harshad has shown in the previous slides, that TMA allows to collect metrics on different levels. And we can leverage this so that we don't collect all the metrics. We just zoom in to the path in the hierarchy that points to the point of performance bottleneck. And this allows for a low overhead of data collection. And the fourth objective is to be able to do real-time aggregation. And that is very important so that we can convert the raw metrics that we collect, such as cycles and instructions, to a higher level, more meaningful metrics that a scheduler would use to adapt the scheduling decisions, such as the utilization percentage and CPR. And now, the first tool that I want to introduce is called the PerfSpec. And PerfSpec is a system performance characterization tool built on the famous Linux Perf. And it is designed to monitor the performance on multiple levels. We can do system-wide, per socket, per core, or even per container performance characterization. It has two main components. One component that is very lightweight, collects hardware events, and follows a template used by Intel. And then there is an intermediate data representation for the hardware events that are collected that is then passed on to the next component, which is post-processing and visualization component. And the benefit of splitting the pipeline of this tool into two components makes it easier for implementing a lightweight hardware event collection and separating it from the post-processing component allows for it becoming extensible to cluster-wide using. So the two components becoming separate allows also for post-processing to inject data from multiple hosts and draw cluster-wide insights. And the tool is open source. You can access it through this link that we have here at the bottom of the slide. The next tool, which is actually part of PerfSpec, but can also be used as a standalone component. It is called the similarity analyzer. And the similarity analyzer has the advantage of the ability to take multiple profiles that PerfSpec generates and compares them and shows in what dimensions, in what type of either front end, back end, retiring dimensions that particular workloads or microservices are similar. And that is very critical for schedulers to identify which workloads should be co-located together on the same host, or which workloads have a high probability of causing interference with each other once we are running on the same. The third tool that we propose here is called the workload interference detector. And this tool performs both performance monitoring and interference detection. It is based on eBPF to monitor and adapt fine-grained performance metrics that are collected on either the process level or the container level. And it sends alerts when performance degrades compared to a baseline, and also identifies what metric is being the hotspot, the cause of the interference, such as the last level cache, so that the scheduler will have a better decision to make with respect to how to resolve the interference. And the nice thing about the tool is that it is highly tunable, so it can be adjusted to different user needs, such as like throughput oriented or latency oriented. It can be used to deconsolidate containers on hosts, or to scale countermeasures to interference above a certain threshold. And the tool is also available in the public repo. You can access it through the provided link here. And the last component of the tool is visualization that the tool provides, which is to export the collected data, that vector of performance metrics that the tool collects for every process or every container can be exported to external cloud monitoring tools such as AWS CloudWatch. And with this ability, it can be used to monitor not just one host. It can also give a cluster-wide vision of performance, and it can leverage the fact that most of the microservices are replicated. So it can collect a signature from every replica of the microservice and use that to estimate a baseline of performance, and then uses that to detect outliers. Those are that perform significantly lower than that baseline. And the additional feature it has is that it has this active notification, so that automatically it will ping a scheduler that is registered, and with that container IDs that are being interfering with each other, and also what metric the containers are interfering for. And again, the tool is made public now, and you can access it through the provided link here. And now we will go back to Harshad to show us a quick demo for our performance monitoring tools.
Hey, thanks a lot, Ashraf. So, we have got demos for multiple of these tools, but we have already put the demos also on the GitHub pages. I'll show a demo of one of the tools here. This is Perspect, the tool that basically uses for performance characterization using the PMU. And as we said, we use the TMA or the TMAM method to say, hey, where is the application bound? Whether it's in the front end, back end, and then you can click on each one of these and zoom into, hey, what aspects of it is it bound, right? And there is also explanation of what these terms are and what they mean. There is pressure stall information and so on and so forth. Once you know where these are bound, then you can get into each of these tabs to understand, the metrics and so forth. I'll kind of play this demo, but it's available on the website as well. I hope it is playing. Okay, looks like. Yeah, so you can look at pressure stall information, get into IO stalls or CPU stalls. Once you know where the stall is, you can look at things like CPI and other CPU metrics, cache metrics, local remote DRAM metrics. There are power metrics if those are exposed, so you can know how much power you're spending. There is a bunch of metadata information towards the end. Also, there's a feature where you can compare data from multiple Perspect collections. So let's say you have collected data on a system, you made a change, you made an optimization, and then you collected it again, you'd be able to do comparisons of multiple data and be able to figure out deltas to know, hey, how are your metrics doing? I know this was a quick demo, but you can find essentially the tool on GitHub as well. So I'm going to come to the summary. So we gave an overview of the microservices architecture, the tight coupling, and how they impact resource contention at a system and a processor level. How observability is very different from monoliths to the microservices. How the architecture has got these, a different set of problems that we need to think of tools that to adapt to, and then because software gets so highly abstracted, we need a way to filter out the view with the help of these tools to figure out, hey, where is the problem? Because of all the layers that software has included in addition, to the hardware and the kernel. So I hope that the overview of these tools that are being developed and open source, and there will be more requests based upon the problems that you see in your area, and feel free to add issues or raise questions on the tools, and we are here to hear them and develop more on them. So with that, David, I think we have completed. I don't know if we are within time, but we are open to questions and discussion.
Excellent. Yes, thank you very much. All a big virtual round of applause to you. It's very interesting coverage. Yeah, we have plenty of time for questions. So please put them in the chat or in the Slack channel. I am not seeing any currently, but let me ask a few that have come to my mind. Hold on, let me just bring up the Slack channel. There's so many channels. There it is. Yeah, no questions yet. So maybe going back to map, I remember that that picture of what I think you refer to as the map step being very interesting, and so much so that I kind of want to try it. Is there a tool available to and maybe I asked this last year. Is there a tool available so that yes, this one, that's great. To me, that seems like a perfect bird's eye view for any complicated microservice or collection thereof.
Yeah.
So, is this possible to generate with the tools that you've just demoed today?
Yeah, so this is part of an ongoing tool, but I think I can still send out an initial link. It is basically based upon the TCP Live tool in the eBPF BCC repository. What TCP Live does is essentially tracks the life of TCP connections between different application endpoints without actually instrumenting the data. So it's a very secure thing. All it's trying to say, hey, I opened a connection, TCP connection, I closed it. How long was it alive and which service was speaking to which? Once you instrument that across the board, you are easily able to generate a chart like this. So today we already have some format of data. We are putting it in a pictorial format for easy representation. So I will try to send a link of this after. Thanks for asking, David.
Sure. Yeah, very cool. So it sounds like anyone can generate the data using TCP Life from eBPF. Is that what you said? Nice. But maybe generating the graph, you'd have to do your own.
There is some more processing involved. Yeah. So
which, yeah, that makes a lot of sense. Very cool. Okay. Any other questions? Yeah, just we had a question.
Sorry,
about
I joined late. Is it possible
you
point us the slides?
Yeah, I was just about to mention that a recording of all the tutorial talks, and I'm almost certain the slides will be made available shortly after. Unfortunately, I don't have specific details about when, but it should be very, very soon. For instance, you can watch all the keynotes from the main conference already. So I imagine it won't take long for us to organize the recordings and download area for the slides.
So I see another question, and I can answer that.
Great. Slack. Yeah. Says, yes.
Sorry, David, to take over here.
No, not at all.
The earliest generations of Intel processors these tools will support? Yeah, that's a great question. Because I know that, if you, even in the cloud or even in on-prem, people have generations old processors, right? So the Perspect tool will provide support from Haswell, Broadwell generations, and that's in terms of Xeon, Platinum. I forget what the naming convention, the marketing naming convention is. But about 4 generations behind. And if there is a need for even further, do send us a request. We can, but we just don't support it in open source because it's very hard to support really, really old systems. However,
Yeah, so Ashraf, I would add, so Haswell is roughly 2014 and Broadwell is roughly 2015. So, you can go back almost a decade.
Yeah, thank you, Doshi. With respect to, it's not just about how old generation processors, it is also important to know that these tools, for example, some of these tools use eBPF, right? So there is a kernel dependency. There's a dependency that you are on kernels that do support those technologies. So the PMUs have been in Xeons or Intel processors for the longest decades of time that we know of, and they are always evolving, like with the processor. But some of the software technologies have software dependencies. So eBPF will have support from, best support from kernel 5.4 and onward. So some of the tools that leverage eBPF would also need that kernel support, if that helps.
Great. Any other questions? If
Can
not,
I ask a question? Sorry.
Please,
can I ask
yeah.
one? Hey, David.
Please
Hey,
do.
thanks for that session. Very good. So I think more to that microservices architecture, I understand that many of these applications are packaged into some containers, right? So it kind of bloats up the code. And you have many of these microservices that maybe are showing out here. So then that brings up this whole concept of every time a microservice is called, which has a big container, possibly it has to be loaded up. So that could be all of these kind of cold start issues on these microarchitectures, plus all the communication issues. And then you talked about some of the kind of the interference if you have too many on the same microarchitecture. How does all that, do you have any insights as to how they play out? I mean, I saw a lot of these graphs, but I was not able to get the insights out of from these graphs.
So good question. I'll maybe try to take a shot first, and Harshad, you can chime in. Ashraf, you can. The startup issues with microservices are very well, and that are a good set of issues to bring up. Generally speaking, what happens is that you leave a microservice running. If you're going to be doing frequent startups with containers, then you are typically going for something like a function as a service type of architecture, where something very rare that needs to run very rarely is run on a trigger. And there you are absolutely right. Startup issues do dominate, and some of the startup issues actually do not even have to do with resource contention as much as they have to do with with various software contentions, right? That happen with regarding setting up the different namespaces of containers. So there has been some work not only by Intel but by also the broad community in accelerating those kinds of things. Also by doing by keeping warm containers around. So things are in a ready to run state, or we can say they are almost like a standing stock, right? So that you can start from there quickly. The larger issue that you are bringing up of continuous changes, right, that occur because you've got a microservice running, but I think what you were hinting at was you have a very large number of them, and how do you really try to?
That's good, and also large number of them, but also each small piece of code has been packaged up into a larger container, right? So maybe I think you're showing some of the monolithic versions in the past, where the whole monolithic code is compressed in like one monolithic code, right? That gets loaded up to in a system, but now each of those pieces of code is broken up, and it has a big kind of a bloat, which is a good thing, right? I understand the microservices concept, but then how does is there a way to make the microarchitectures? I don't know. Is there a way to build it or define it in a way that it can take care of this larger bloat? Like, do you need larger caches, more cores? I'm just thinking through this as I'm hearing your presentation.
Yes, so our focus today was on making it easy to understand where your bottlenecks are, so that you can take some responsive actions. On the longer term, right, in companies like Intel, right, are very much invested in tracking such trends as microservices as well as AI, and then potentially a combination of the two.
I think I can really do it until I'm there anyway. So really, it's more like, I'm just not sure.
If we could all please mute besides those speaking, that'd be very helpful. Let me see if I can. I think it was Paul. Okay.
Okay, so just continuing on that answer, right? The point about optimizing microservices, microarchitecture for microservices, is definitely a good one. It is just that that wasn't the focus today. The focus today was on how do we make how do we make progress towards solving the problems with the software challenges that we have today. But your point is good, and I think companies like Intel are definitely looking into it.
And if I may take another shot. So yeah, I mean, you were talking about this monolith and being driven into these different pieces, but I've seen different when adoption of microservices happens, you can go into different levels of this. In the first level, you might just split these microservices and then have a separate cluster running each one of these separately, right? So you're breaking some of the CPU contention into network load. And later you might actually see that because you want to have a better TCO in the cloud, you might start again bringing some of these back into a physical node just because you want to pack as much as possible. And those are the aspects where we are talking about. Then when you're trying to do this, it's not just about, hey, I'm just running 40% CPU, I should be able to pack more of these, right? It's not about that, because you need to have a view of what the contention and what resources you're really using to be able to, and we are trying to decipher that all the way in pieces here. Okay.
And the communication aspects, you're talking about communication. So are these like data communications, or are they message communications between the microservices?
All of them. It could be the control plane, it could be the data plane, but because you generally, when you split this, you have an orchestrator, right? If you had Docker containers, you have something like a Kubernetes or a Mesos.
Correct.
That would have a control plane, as well as I'm talking about the data plane, because now you have split things. Instead of doing memory access, now you're going to do it over the network.
Okay. And so when you're doing this analysis, can you also capture that communication latencies?
Yeah. So what I showed as that map that David was talking about, that was actually those were communication latencies that were happening. Now, communication latencies can be on the same platform. It can even be on different platform over different geos. Yeah.
Okay. And each of those bubble was a microservice, right?
Exactly.
Okay. Well, thank you.
Sorry, I should have said. I think I ran fast through it.
You may have said it, but I think I missed it, right? So I think each microservice gets an IP address when it runs, correct, right? Exactly. So it becomes, okay, all right, got it.
So it could be on the same platform, it could be on different platform, it doesn't matter. It still has to communicate with each other over a protocol, right?
Even though it's on the same platform, it has to communicate to the IP address. So it might be going up to that kind of a layer 3 network and then coming down. Even though it's on the same platform.
I mean, it depends on the protocol, but yes, it could be. Okay. It might be faster access, but it still has to obey the protocol rules.
Okay, got it. Thank you.
All right. These are great questions, great conversations. Thank you so much, Harshad, Doshi, Ashraf. That was fantastic. I encourage everyone to join the next session. So actually we have to leave now and go to the next session, despite it being presented by the same team. But yes, again, thank you very much. Virtual round of applause, and we'll see you in the next one.
Thank you.